All right, so these are the sample problems from chapter 7. All right, so so the first thing is we've got the mass. All right, so the density, of course. Let me write the equation down real quickly. The density, which is the symbol rho, is the mass divided by the volume. All right, so in the when we do this, the mass has to be in kilograms. I'm sorry, the mass has to be in grams. All right, and the volume is given to us in centimeters cubed. All right, so they gave us the mass in kilograms, so we have to change that, and we know that kilogram, 1 kilogram is of course 1,000 grams. Okay, 1,000 grams. All right, so what we do is we say, all right, well, the mass is given to us as 0.9, what is it, 974. Let's make that decimal a little bigger, 974 kilograms. And then we just use this conversion, right? We say, all right, well, I got to cancel the kilograms. So I put 1 kilogram in the denominator, and I put 1,000 grams in the numerator, right? The kilograms cancel, and so that is, so you multiply this by 9, the 0.974, it becomes 974, right? So it's 974 grams. All right, and then the rest of it's really easy since you have the mass and it's now in grams. The volume was given to us right here, and it's already in it's already in cubic centimeters. So you'd say that, of course, the density is let's see. So it's going to be 974 grams divided by the volume, which is 295.15, and it's of course centimeters cubed. All right, so and usually, by the way, you're not directly given the volume the way we were here, but anyhow, all right. Let's go ahead and do this problem. So here's our scientific calculator. If I can get it to move, there we go. So it's 974, right? 974 divided by 295.15. All right, so there's the division, and when we do that, we're going to round it to one place past the decimal. So that's how we get this 3.3 grams per centimeter cubed. All right, so that's given to us. The answer was given to us. All right, let's move on to the second one. Okay, so there's our second problem. I don't know why it says 1 right here. Anyhow, it says, so like everything in orbit, our moon travels in an elliptical path. The point where the moon is closest to the Earth is called the perigee. By the way, when the phase of the moon, when this happens, when the phase of the moon is full, the phase of the full moon can happen at any point, but when the full moon occurs and the moon is also at perigee, then you have what we call a supermoon. That's just a side. That's a side. All right. So it says, suppose the radar beam from Earth bounces off the moon and returns, and the round trip time is 2.422 seconds. How many kilometers is the surface of the moon away from the surface of the Earth, which is that's where the radar beam was originally sent? All right, and we want it to be in kilometers, and there's the proper answer. All right, so let's go ahead and do this. We'll, I don't know if you really need a picture, but okay, so here we are. Let's say you're on the Earth, right, and you send up, and then the moon is like way over here. All right, so you send a radar beam, it travels out to the moon, and then bounces back. All right, so here's the radar beam bouncing back. All right, so the time it takes to go there and come back is given to us. And so that's called the round trip time. All right, I'll call it T round. All right, the round trip time. And that's given, oops, equals, that's given to us as, right here, 2.422 seconds. So very precise time, and we can actually measure it a little more accurately than that. But that's good enough. All right. What we're going to do here, of course, is the distance to the moon. Okay. So we're interested in this distance here. So we're interested in d. All right, is going to equal. So it's really the round trip time, right? Round trip time divided by 2, right? Because the light, the radar beam, which travels at the speed of light, goes there and then comes back. So we only want to know half that time, and we multiply that times the speed of light. So that's a c, right? And of course, c is 3 times 10 to the 5th. All right, so here we go. So d is equal to the 2.422 seconds, all right, divided by 2, and then we multiply it times 3 times 10 to the 5th, and of course, it's kilometers. I might have said meters. I didn't mean to. Kilometers per second, all right, and notice the seconds cancel, and so that'll give us an answer in kilometers, all right. So let's get our scientific calculator, and we'll take a look at this. And of course, we already know this will be the answer, all right. So, oops, that's the wrong thing. I didn't mean to do that. There we go. All right, so clear that. All right, so 2.422 divided by 2 equals, all right, so that's the time it takes the radar beam to reach the moon, and then we multiply that times the speed of light, which is 3 times 10, and there's, let's see, so yeah, we use the EXP button to the 5th, right, and that's the 3 times 10 to the 5th kilometers per second, all right, and this, of course, the seconds canceled, as I showed you right there, and so that will give us, well, look, exactly the number that we got right there. 363,000, 363,300 kilometers. All right, so that is indeed the answer. All right, let's do the next one. All right, so here's our third problem. Suppose the circular crater Tycho, which, by the way, has a diameter of 85 kilometers, so suppose, yeah, anyhow, I didn't word this very well. So the crater is 85 kilometers. Could a person see the crater with the unaided eye? Show your work for any credit. The smallest angular size that the human eye can resolve with the unaided eye is 0.5 arc seconds. All right, so we're going to see, and of course we know the average distance to the moon is 384,400 kilometers. So let's see if if humans could actually see this. All right, so if the number that we come up with is smaller than 85, then you'd be able to see it. Okay, so all right, so anyhow. So what we're going to use is this angular size, right? So remember this script L is equal to pi over 180 times the distance to the object. Of course, we have the distance times this thing called alpha, where alpha is the angular size of the object. Okay, so let's say that we're at the very limit at which humans can resolve something. By the way, resolving is like if let's say it's I don't want to go too much into this. If you are driving down the road late at night and there's some headlights coming at you, if the road is really, really long and the car is really far away from you, you actually can't tell the difference between whether there's two headlights or one. And so as the car gets closer to you, that's the point where it's close enough that you can resolve it into two headlights. That's this angle alpha. All right. So anyhow, that angle. The one thing that we have to do is we've got to change it to degrees. All right. So alpha here is 0.5. Of course, remember arc minutes. You can use a single hash mark, and then of course there are in 1 degree there are 60 arc minutes. All right. So it's just 0.5 divided by 60. That's what our angle is. And then we multiply by d. We multiply by pi, and we divide by 180, and so we can do that. And so it's going to turn out that this thing. Let's see, where do I have it? There it is. It'll be so with the unaided human eye, you could see a feature on the moon at this distance. You could see a feature on the moon at 55.9 if it was 55.9 kilometers. All right. So here, let's do this problem. The first thing is take 0.5 divided by 60. All right, so this is our angle in degrees. So really tiny angle. So we're going to multiply that times the distance to the moon. All right, so times 384,400. And then we multiply by pi. All right, so times pi. And then divided by 180. All right, 180. All right, so again, we're looking for a number. If it's smaller than what Tycho actually is, remember L is the actual size of the object. All right, so this is going to tell us the minimal size that the human unaided eye could see. So it's 55.9 kilometers, right? 55.9 kilometers, which is exactly, that's what we have. Tycho is bigger than that, so you'd be able to see it. However, just to let you know, it's in the southern part of the moon. It's actually not easy to see with the unaided eye. It's not like it's standing out. It's actually easier to see using a small pair of binoculars or of course a telescope. All right, let me try to get the next problem in. All right, so here's problem number 4, the last of them. There will be other problems. I just wanted to get through this set. All right, so what is the average density of the moon in grams per cubic centimeter, round to one place past the decimal? You're given the moon is 7.35 times 10 to the 22nd kilograms, and its radius is 1,737.4 kilometers. So we got to get everything in the proper units. Of course, this is the volume equation for anything. Oops, I didn't write the R in there. R cubed, right? So this is the volume equation. The mass has to be changed from kilograms to grams. There are 10 to the third. That's supposed to be a 3. 10 to the third kilograms in 10 to the third grams in 1 kilogram. The kilograms cancel here, and so you just when you have 10 to the 22nd and 10 to the third, it becomes 10 to the 25th. All right, so we take then this is the one the part that's kind of tricky. You take a 1,737.4. 1 kilometer is 10 to the third meters, and the kilometers cancel, and then 1 meter is 100 centimeters, or 10 to the 10 to the second. So 10 to the third times 10 to the second is 10 to the fifth. All right, I'm running out of time. Let me try to do this real quickly. Okay, so I've got this here. I'm gonna pause. So there's my volume. There's my radius, and I have to raise it to the third power. So I let's see. Oh yeah, Y to the X button. So I raised it to the third power. All right, so that's cubing it. All right, so this is some huge number, but then, oh man, I'm running out of time. All right, so I put everything in. So that's the mass divided by, and I already stored the answer, equals. All right, so 3.3. That's the correct answer.